carboxylic acid. The other conditions would afford us an aldehyde. And so those second conditions would use PCC, pyridinium chlorochromate. And those reactions are usually carried out in dichloromethanol. So this is the oxidation step that takes us from primary alcohol to an aldehyde. Right? And then at this point, this carbon becomes an electrophilic carbon. And we can add different nucleophiles to that depending upon what we want to add to the molecule. Here you can see we need to add a phenyl group, right? So phenyl grignard. In some ethereal solvent, we'll say diethyl ether. And then we have to work this up with water and a little bit of acid. Add the proton onto the oxygen.
So a grignard would cause it to would cause the carbonyl to split. It's like
The grignard?
yeah. I was confused as to how it could be 3 steps. I thought it had to be 4. Because when you would add the phenyl grignard, which I thought it would turn into 2 phenols with a carbonyl in the middle, then you have to add a reducing agent to get it to.
No, so the grignard is essentially reducing the carbonyl, right? So mechanistically, what's happening? Right, so it's the electrons between carbon and magnesium that are nucleophilic. So those will add, right, the carbon-oxygen pi bond, right? So that's essentially the reduction, right? Replacing a carbon-oxygen bond with a carbon-carbon bond. And that gets to that intermediate, and then the workup just protonates the oxygen. Questions about this? So let's just really quickly review the 2 types of oxidation we went over the other day. So the first one was Jones oxidation. And Jones oxidation involves the addition of a primary alcohol, or the treatment of a primary alcohol with chromium-6, right? In this case, sodium dichromate, sulfuric acid, and water, right? The oxidant, so this is the oxidant, chromium, right? The oxidant that we're putting in can come in a couple of different forms. This is kind of the standard form that you could buy from Aldrich, sodium dichromate. You can also buy CrO3, so chromium trioxide, chromium-6 trioxide, which is what happens, what forms whenever you mix sodium dichromate with sulfuric acid, right? So we either add it directly or make it in situ. This is a form of chromium that's easier to handle. But we'll go over the mechanism in a second. Right? And so when we oxidize a primary alcohol, that leads us to a carboxylic acid. Okay? And if we treat a secondary alcohol under those same conditions, afford us the ketone. Right? In contrast, we also looked at PCC oxidation. Right? And the difference in terms of products is pretty significant, right? And it really comes in the oxidation of the primary alcohol. So whereas Jones oxidation will give us the carboxylic acid, PCC oxidation of primary alcohols will afford the aldehyde. Right? And then if we have time today, there's going to be one other oxidation that we go over. We can also oxidize secondary alcohols with PCC, but they give us ketones. So there's no difference in product with secondary alcohols. All right, so let's take a look at the mechanism of the Jones oxidation to see if we can understand.
Question. Jones and PCC oxidation. Can you only do the first and secondary alcohols, but not?
Yes, yeah. So if you look at these, right, what's happening is we're replacing bonds with hydrogen to bonds with oxygen. Right. So if we have a secondary alcohol, we only have one hydrogen, right? So we can only make one more bond to oxygen. Tertiary alcohols, no hydrogens. Yep. All right, so if you take sodium dichromate, treat it under acidic conditions, sulfuric acid, this doesn't have to be in water because we generate water when we do this reaction. We make chromium trioxide, all right? One really important thing is the oxidation state of chromium. So we're starting with chromium 6. So if we are oxidizing a carbon, right, it's the chromium in this reduction that's getting, or in this oxidation that's getting reduced, right? So the chromium is doing the oxidation, the chromium itself is then getting reduced. Okay. So when we go through this mechanism, what's going to happen is the oxygen of the alcohol is going to add to the chromium. Okay? And that's going to break one of the chromium oxygen pi bonds or double bonds. undergo proton transfer. Right, and then this next step is kind of the critical step in the oxidation. Right, so this is the point where the carbon gets oxidized and the chromium gets reduced. Right, so we'll show a chromium-oxygen pair of electrons from chromium to oxygen reaching out to grab this proton. Those sigma electrons falling down to form the pi bond, right? So that's the carbon oxidation. And then electrons are being given back to chromium for the reduction of chromium. Right, and so you can see in this oxidation of carbon, we're going from chromium 6 to chromium 4. Right, so starting with 6 bonds to chromium, and we're ending, you can see the chromium only has 4 bonds going to it. Questions about this so far? Okay, so important to note. So most metals have can exist in different oxidation states. Okay, but also most metals can not exist in some oxidation states, right? Or some oxidation states for metals are so unstable that they're not going to last very long. So for chromium, the 2 major oxidation states, the 2 stable oxidation states are chromium 6 and chromium 3, right? And these are, the thing about inorganic chemistry is that it's kind of pretty. So chromium 6 is going to be orange, and chromium 3 is going to be a blue-green color. Right? And whenever we do this reduction, chromium 4 is not stable. Right? And this is going to basically undergo a reaction where it eventually ends up as chromium 3. We're not going to really go over what happens exactly to the chromium, right? But it splits into chromium 3 and chromium 5, and then the chromium 5 is oxidatively active. But anyway, what you need to know is by the end of the reaction, all of the chromium is reduced to chromium 3, right? And so we can visually track this reaction just by looking at the change in color, right? It starts out as an orange color, and when the reaction's done, it goes to blue-green. So it's a nice visual indicator of what's going on. Okay, so we get to this point, right? We're starting with primary alcohol. We know primary alcohols get oxidized to carboxylic acids. We're not there yet, right? We have our aldehyde. Right? And we have that aldehyde in acid and water. So what's going to happen to that aldehyde in acid and water? Not an acetal. We need alcohols to form the acetal. It's an equilibrium reaction, right? It's not something that we can pull out of the reaction and store in a bottle. It's always going to be an equilibrium. Yeah. Excellent. Yeah. So we have to realize that aldehydes, when in the presence of water, are going to exist in equilibrium with their hydrate, whether we want them to or not. Right? It's not our option. Usually not an intentional reaction. right? But when you look at the structure of the aldehyde and the aldehyde hydrate, hopefully you can reason that just like an alcohol can add to chromium-6, right? Through its hydroxy group, an aldehyde hydrate can also add to chromium-6 through its hydroxy group. Right, so we'll go through a couple of mechanistic steps, right? Just like we did up here, right? We're taking a hydroxy group, adding it to the chromium trioxide, right? We form this intermediate. There's a proton transfer where we're transferring a proton from the oxygen that we just added to the oxygen on chromium that forms a negative charge, right? And we get to this point. So that's what I just represented with these two arrows, right? Showing both of those steps in one. Right, so at this point, we can undergo that same oxidation reduction. Right, so carbon gets oxidized, chromium gets reduced, and that takes us then to carboxylic acid. Questions about this mechanism? So as you can imagine, I mean, if you look at the conditions of this reaction, this is a somewhat, we're somewhat limited to when we can use this oxidation, right? The conditions are rather harsh, sulfuric acid and water. Organic molecules typically are not soluble in water, so we'll often need to create a more polar substrate in order to carry out this Jones oxidation. Chromium is not, chromium-3 is okay, but chromium-6 is really not good for you. Has everybody ever seen the movie Aaron Brockovich? I feel really old when I mention this. It was a movie that came out in the 1990s, maybe the early 2000s. Julia Roberts, she played the role of a lawyer in California who was investigating poisoning in a city of Hinckley, which had, that's where Pacific Gas and Electric had a station, a power station. And one of the things that they used to treat the equipment out there was chromium-6. Chromium-6 leached into the groundwater and poisoned a bunch of people. So it's a really bad chronic carcinogen, actually. Really great at preserving metals, which is why industry will use it, but if it leaches into the groundwater, then it's really bad. Anyway, it goes over chromium-6. All right, but in terms of organic chemistry anyway, Jones oxidation is a great oxidation, right? But it's hard to control with primary alcohols, really harsh conditions, right? So there's a chemist at Harvard, organic chemist named E.J. Corey, who developed a reagent called PCC, pyridinium chlorochromate. We looked at the structure the other day. So this is also a chromium-6 reagent. You can see the structure of it is pretty different from the Jones oxidant, from the dichromate. So if you look at the Jones oxidation, why do you think we have to use water as a solvent? Or why would you think we would need to use a really polar solvent for that reaction?
There is a lot of proton transfer.
A lot of proton transfers, but if you think about the structure of the oxidant that we're starting with, right, dichromate, or even the chromium trioxide, what do you think about the relative solubility of that material in an organic solvent versus water? Yeah.
It's extremely polar, so it wouldn't be soluble in organic solvents.
Yeah, there's nothing organic on chromium trioxide, nothing organic on the dichromate, right? It's ionic, the dichromate, right? So we wouldn't expect it to be soluble in organic solvents. And that's one of the reasons why we need to use water, at least as a co-solvent, for this reaction. And because water and acid are always going to be in this reaction, right, this hydration is going to take place whether we want it to or not, right? We're going to form the aldehyde, there's going to be water and acid in that reaction, and this equilibrium is going to be established whether we want it to or not. Pyridinium chlorochromate, right, also a chromium 6 reagent, but you can see we have this organic pyridinium ion, right, which is water soluble for sure, right, but it's also organic, and so it's going to be soluble in organic solvents. And so we can do this reaction in dichloromethane. Dichloromethane, as you've learned, is a really great solvent if you want to not have any water in your reaction. Right? Water and dichloromethane don't really mix at all. So whenever we do this, right, we oxidize the aldehyde. Right? There's no water in this reaction. Right? So no hydrate can form. And if no hydrate can form, that second oxidation is not going to take place, right? Because in order for the second oxidation to take place, we need one of the hydroxy groups from the hydrate to add to the chromium trioxide. And if we're not forming that hydrate, then we don't have to worry about that second oxidation. So your assignment for the weekend is to watch these two movies, Aaron Brockovich and Fight Club. Fight Club we mentioned last semester. Both really great movies. So have a very loose connection with chemistry. All right, so any questions about PCC? So everybody understands why Jones oxidation takes us all the way to the carboxylic acid. PCC allows us to control that oxidation a little better and stop at the aldehyde. Right? So it's, that's a pretty important thing to be able to do, right? Have options for how far we want to oxidize things. Questions? Okay, so the third oxidation that you're going to learn is an oxidation called the Swern oxidation. And we're not going to go over the mechanism of this, because I want to get through a couple of other things. But the mechanism is in your book, so please, over the weekend, when you have a chance, take a look at the mechanism in your book and see if you can understand it. And the big feature of this oxidation is that it's chromium free. As we chemists think about the impact of the chemistry that they do, it's becoming more and more important to have greener protocols. And anytime you can avoid using heavy metals, particularly heavy metals that are going to just go into waste, that's a good thing. Good thing for the environment, good thing for our health as well. So Swern oxidation is chromium free. And just like PCC, it can take a primary alcohol and oxidize it just to the aldehyde. So DMSO, if you don't remember, okay, so it's kind of a, I don't want to say it's two-step, but it includes the addition of reagents at different times. So when we start this reaction, we add the what's called oxalochloride, right, in our DMSO. We let that mix, let that react, right, and then after a little bit, we squirt in triethylamine or some other hinderedamine base, right, and that's going to affect the oxidation, right. Whenever we oxidize, just like with the chromium oxidation, right, whenever we oxidize carbon, we have to reduce something else, right, so something, those two things are always in balance, right, if something is being oxidized, something else is getting reduced. So this is kind of an interesting reaction because the thing that's getting reduced is the DMSO, right? And the DMSO is reduced from dimethyl sulfoxide to dimethyl sulfide. Right, and so this reaction is going well when it really smells in your lab. Right? So dimethyl sulfide is a really stinky chemical, really volatile chemical, and yeah, you can smell it even if you have the hood sash down. Right, that smell is really pervasive and it doesn't smell. So whether that's a good thing or bad thing, I don't know, but it tells you your reaction is going. All right, so when you have a chance, like I said, take a look at the book, look at the mechanism, make sure you can at least follow it, right, and try to understand it as best you can. And if you have questions, just let me know. Okay, questions about oxidation? Okay, so right, we spend time writing all of these mechanisms on the board, and I think it's important to stop every once in a while and think about how do we actually know these mechanisms, right? How do we know the electrons actually move that way? And there are different tests or different experiments that we can carry out to help us, or at least point us in the right direction, or suggest that a mechanistic pathway is possible or impossible. So a colleague of mine worked with a student, or a colleague of mine at Pomona College out in California worked with a student in high school to make this video on a method called kinetic isotope effects. And I'll show you that video.
Nostalgia can help you remember ads. So customize and save with Liberty Mutual.
Ready? Wow. Mia, can you send me that? Sure.
A visual isotope effect, the chromium-6 oxidation of 2-propanol. This demonstration uses time-lapse photography to compare the chromium-6 oxidation rates of 2-propanol and 2-propanol D7. Experimental design. The alcohols are added in rapid succession to each of the 2 vials containing the light orange chromium-6.
So just real quickly, right, the thing that's important, and I think the speaker will go over this difference, the thing that's important, right, in the mechanism, that hydrogen that's highlighted here and the deuterium that's highlighted here, right, those are the atoms that are undergoing change or being plucked in order to affect that oxidation, right? So it's the electrons between the hydrogen and the carbon that help to oxidize, or that create the pi bond, or the hydrogen and or the deuterium and the carbon that create the pi bond, right? So having this difference in isotopes, if that atom is involved, will this test will give us information about the reaction.
This reagent. A third vial at left contains no alcohol and serves as a control. A color change is used to monitor the reaction rate. The light orange chromium-6 is reduced to chromium-3, which is blue. On the next slide, you will be able to see that chromium-6 has begun to react with the alcohols. This first shot was taken approximately 30 seconds after the reactions began. Therefore, 0 seconds is when the photo started, but not the reaction. Here is the first shot of the experiment at approximately 30 seconds after the reactions began. We ran the experiment for 90 minutes and took a photo of the vials every 10 seconds to document the reactions.
So remember, there's a color change, chromium-6 to chromium-3 from orange to blue-green.
We have stopped the time lapse at 1000 seconds to show you that the middle vial with 2-propanol has completed reacting, while the vial to the right with 2-propanol D7 continues to react with chromium-6 for the next 4400 seconds of the experiment. For your convenience, we have sped up the remainder of the time lapse, and at its conclusion there will be a brief explanation of what is happening in the vials. The sample containing 2-propanol D7 reacts more slowly than the vial containing 2-propanol. Now you might be asking yourself why this is the case. Well, the difference between the 2 alcohols is the presence of deuterium, one of the 3 hydrogen isotopes. With 1 proton and 1 neutron, deuterium is twice as heavy as protium, the most abundant hydrogen isotope. The larger mass of deuterium causes C to D bonds to be shorter and stronger than C to H bonds. This difference in bond strength is due to a mass-dependent quantity known as zero-point vibrational energy. If a reaction rate is thought to depend upon the rupture of a C to H bond, then this hypothesis can be tested by replacing H with D and seeing whether or not the reaction rate slows. The oxidation mechanism consists of 2 processes. The first is formation of a chromate ester. This process consists of several discrete reaction steps typical of acid-catalyzed esterifications. The second is the actual oxidation-reduction reaction. In this step, a C to H bond is broken and a pair of electrons is transferred from 2-propanol to chromium. 2-propanol is oxidized to acetone, and chromium-6 is reduced to chromium-4. Chromium-4 is a reactive species, which undergoes further reduction to chromium-3. Which process determines the overall rate of the reaction? Because the deuterium-containing alcohol slows the reaction rate, this suggests that the second step is rate determining, or the slowest step of all the processes. The other steps are rapid by comparison. This is because the second process is the only one in which a C to H bond is broken. The rate slows because the stronger C to D bond is more difficult to break. This is called a kinetic isotope effect. Chemists can use information like this to understand how chemical reactions work. Researchers in the late 1940s, in fact, used the approach demonstrated here to confirm the slow step of the chromium-6 oxidation process. They determined that 2-propanol D reacted about 6 times more slowly than unlabeled 2-propanol. We use 2-propanol D7 in our demonstration because it is less expensive than 2-propanol D. The two CD3 groups in 2-propanol D7 do not contribute much to the isotope effect, so the two labeled compounds behave nearly the same. In conclusion, time-lapse photography can be used to demonstrate the different chromium-6 oxidation rates of 2-propanol and 2-propanol D7. Because the isotope effect in this process is large, the effect of deuterium incorporation in the system is readily visualized. This slide shows the sources that were used in this presentation.
I don't think it was so like I got up like Tuesday morning, and then Wednesday I was fine. So it was really weird. Yeah. So with the lab, I wasn't able to make it on Tuesday.
Rebecca and Kavya could also run the reaction. So I'll probably have the three of you run the reaction together, and then you can join Joey and Courtney's starting next week. So you just get some experience.
Okay. When do you think?
If you guys want, try to get in touch with me and figure out when you can come in. Monday morning would be an option. Or Monday evening would be an option. The advanced lab uses 2049, so there are only 4 of them, so there will be space. So really anytime Monday.
I can make one. That's good.
I mean, the reaction setup is it takes not a lot of time to set it up, like 45 minutes, and then the workup is kind of the longer part. So it's got to go for at least 12 hours or so, and then working it up. It's just doing a bunch of washes and using the sample. So it shouldn't take that long, but if you have to slip on for a while, then
Okay, yeah, that sounds good. And what is your name?
Copy.
Okay.
Yeah. So when I get back to my office today, I'll send it to you.
That works. Okay, sounds good.
All right.
Yep, thanks.